So thanks for joining. My name is Tomas Petricek, and I'll be talking about designing composable functional libraries, not just for data visualization. I work at University of Kent, and I do some F# consulting at F# Works as well. So this talk is sort of it's using a domain that may feel strange to people or may feel unfamiliar. But really, the point is to talk about functional thinking and how you think as a functional programmer. And charts I'm using as an example because they provide a really nice playground for explaining those ideas. So the motivation for this is not so much technical. It sort of came from a project that I've been involved with, which tries to make data exploration more open. So the motivation is, and you see more and more journalists these days are actually using data in news reporting, and often they'll have interesting charts, and as a programmer or as someone who could actually check whether they've done it right, you always keep wondering, how did they actually do this? So I've been working on a project that, to put it in this way, makes facts great again and lets people sort of see how things are, how data visualizations are created. And as part of that, I wanted to create some interactive data visualizations. And obviously, as a programmer, when you have a problem and you can't quite find a perfect solution for it, you wonder, what would it take to write my own data visualization library? And that got me really to think about what is a chart. If you want to create a nice composable data visualization library, you really have to understand what is it that you're working with. So the main point of this talk is going to be about that. It's going to be about how do you look at this interesting and tricky domain and make sense of what is a chart so that you can have a nice API for working with that. So I'll be using the charts as an example, but really the main point is all these different sort of tricks and tips that help you with functional design. And I'm going to be doing this in F#, but I think actually many of those ideas are useful regardless of whether you're using functional programming language or not. So if you start looking at what is a chart, the sort of first place you go to is something like Google Charts, and that's just a popular charting library. And their answer to the question of what is a chart is this very long list of things. You can have bar chart, column chart, line chart, scatter chart, histogram. Then they have things like combo chart, which actually is a sort of strange combination of some predefined charts. But as you see in the screenshots, there's just a long list of things. So this makes you think, well, maybe there really isn't any sort of deeper structure to it. Maybe if you want charts, you just have to create 20 different types and then people will pick. So that's not very satisfying. And it also doesn't cover many of the really interesting things. So my favorite example of a data visualization is this, this thing produced by the New York Times, where what they're doing is that they're looking at the history of Olympic Games and what countries won what number of medals. And it's just a really nice way of telling the world history, because you can see the two gaps there for the First and Second World War. You can see during the Cold War era, the boycott of first the games in Russia by the US and then vice versa. So you can see the sort of rise of countries outside of Europe and US towards the end. So it really tells a nice story. But if you start thinking about what this is, well, is there any sort of deeper structure to this? Or maybe a chart is really just the SVG graphics with some text and shapes that you have to the positions of which you have to calculate manually. So that's not very satisfying. So when people write charts and create charts using charting libraries, you basically have two options. Either you go for something very low level like D3, where you just define points, you use some functions to translate them to pixels, and then you generate some DOM elements and set their values, and that's your graphics. So that's really tedious. But it lets you do anything you want. The other option is to use something like Google Charts, where you just say, I want a bar chart and a line chart together, and that is easy, but it doesn't let you do anything interesting. So it gets even worse when you start thinking about interactivity. This is another nice idea of from New York Times, where what they did is they created a chart where they only show you some of the data and you have to draw the rest to make a guess. And then they'll say how wrong you were, which is a great way of making you think about the problem. But once you add interactivity, something like Google Charts doesn't really help you anymore. So you have to do a lot more programming. And how do you represent that becomes another big question. So when you sort of go through these ideas, you'll really see that there's some common things that are important about charts. There's some kinds of projections where you have domain values, say a country like United States or the UK. You have domain values like 200 members of parliament that you have to map to pixels. Then you have some shapes, obviously, filled areas, lines, and so on. And then there's various ways of composing these. And then the interactivity is adding this sort of dependence on user input. So user can interact, and then the state of the chart will depend on that. So those are some things that we have to represent in a clever way. And what I'm going to do is I'll talk through a couple of examples that demonstrate a library that I've been working on in F# that really sort of shows you how you build up a chart from very small, very basic pieces. So I'm going to switch over to code here, right? That's my demos, and I've got some sample data. I've got UK elections and exchange rate in June 2016. And I've got a page here where we will see the outputs. And the basic thing I can try to do is to say, I want to create a column chart with the election results. And I can just start by creating a new column. And I'm going to use the F# pipe to render this. So I create some shape and then render that. If I save it, switch over here, it turns gray. So that's not very impressive, is it? But the point is, I haven't really specified anything about this chart. I just said I want one column. And what happens is that the column takes up all the available space. So there's one column taking my entire screen using default color with no axes. But we can do more. And the first primitive I'm going to be using is this layered operation, where I can say, I'm going to iterate over all my data. And for every party, I'm going to create a column with the party name and the election result from 2019. And I'm going to overlay this. I'm going to fix my typos. I'll save this. And now you see it actually starts resembling a shape of a column chart. So gray boxes of different heights. So that's getting better, and that's just done by overlaying these basic columns. Now we want to make it more interesting, so I'm going to add some color here. That's the first step, and now it's colored, so you can already guess if you know the UK politics. And I'm going to do my last bit, which is to add some axes, and I have to say on which sides I want them. So I'm going to add axes over the whole thing I just constructed. And if I do this, now I actually get the normal column chart. So the point here is I've sort of started from very simple basic blocks, like just a column that represents one of these boxes here. And from that, I was able to construct a complete chart in just a few steps. Now, the key thing here that was really interesting is this handling of continuous and categorical values. So I didn't say much about this, but when you look here, a column, here I say this is a categorical value, and then I give it a string. And here I say this is a continuous value, and I give it a number. And if you look at this chart, the y-axis is continuous, so there's numbers from 0 to 400. The x-axis is categorical, so it just has different categories, in this case, party names. And the library behind this is sort of the first thing that really is a fundamental basic primitive here. The library behind this handles or understands those values and does clever alignment. So on a continuous scale, you just have values from 0 to something. And when you have a value on that scale, you know where to put it. On a categorical scale, this is somewhat more interesting because you have these separate categories and they just get sort of put side by side, one after the other. And within each category, you actually have a sort of range of positions from 0 to 1. So you can uniquely say where on this chart I am, for example, by saying sort of green 0.3, that will tell you this coordinate here. And the beautiful thing is you sort of try to understand what a chart is by thinking about it in this way. And at the same time, you can write F# code, F# type definitions that represent this. So in my case, there's a type for scales, and scale can be a continuous that represents sort of area of a chart, really, from some number to some number, or a categorical, in which case it just has a list of these different categories. A value can be a continuous, that's a number somewhere on that continuous scale, or a categorical, in which case it's the name of the category together with a position where in that area you are. And a column chart, really, you could see I was typing derived.column. That's because it's not a primitive thing. A primitive thing is just a filled shape. And here, for example, this one starts from labor 0 and goes to labor 1. And the y-axis is from 0 to 200 something. So this is sort of one case where you have to understand what is it that you're dealing with, and then you can nicely represent it as discriminated unions. The other type I'll show you is a definition of a chart. So this is really sort of trying to capture what is a chart. And here I've got basic things like a shape. Now, a shape is a sequence of x and y coordinates, and that's just points in a shape that will get filled. Then there's various transformations like axes, which take a shape, and 4 booleans specifying where you want to put the axes. You can add padding, things like that. The key thing here is layered, which takes a sequence of shape and sort of puts them all together, automatically aligns them. And that involves doing things like figuring out what's the individual scales of those shapes, how they compose to one scale that you can then use for the whole chart. Now, to do a little bit of tiny advertising for F#, I think there's one thing that's been really, really valuable that people don't often know about F#, and that's the fact that F# has units of measure. So this is a mechanism where you can say, I have a number, but it's not just a float, it's float of some unit. It's float of kilograms, or float of years, or float of members of, or probably int of members of parliament. I don't think you get half member of parliament. So in my type definitions, what I've been using throughout is annotate these shapes and values with whether they represent the X or Y axes. And this is great because then in your code, if you mix up X and Y's, it will tell you this doesn't compile. And it's also great because you then end up doing some pretty tricky calculations that I never learned in high school, like how do you project from a space to another space. And with units, the project function is really just something that takes a scale of X units, scale of Y units, value of X units, value of Y units, projection from one kind of X units to another kind of X units, and produces values in the other kind of X units. So typically, if I've got a chart that talks about years, and I'm projecting that to pixels, this will make sure that the value I calculate actually is in pixels. So this is a fairly sort of technical F# thing, but it's just been hugely valuable and useful in defining the domain so that you can make sense of it. Now, I want to show you another chart. And as you can see, people living in the UK just can't give up on Brexit. So I've got another example here. I'm going to create a line chart that goes over some exchange rates between, what is this? Pound and dollar. And I'm just going to start by drawing a line and rendering it. And I forgot one more thing. So I don't have dates for those values. It's just a plain list. So I'm going to use indexed to add just a number from 0 to 1. But the chart you see here now is a line that represents the pound-dollar exchange rate around the 2016 Brexit vote. And what I want to do now, and that's a thing that not many charting libraries let you do, is put some background that distinguishes the part between the vote and after the vote. And so I just really want to have some background there, but this is already something that, for example, in Google Charts, you can't do. So I'm going to make this, so black. So I've got a black line. And if I want to put some background, what I'm going to do is just use my shape layered construct for putting multiple things over each other. And I'm going to take my line and combine this with a shape that's just a filled shape with some number of points that define the corners. And the points I don't have to specify in pixels, I specify them in the domain values. So my X is 0, that's just the sort of number of the days. And my Y, the second thing, I think I want first, what is it, 16 days? And my Ys are actually the exchange rate. So this is going to be drawing from exchange rate 1 to 1 to exchange rate 1.8, I think. That looks nice. And go back to 0 day I just had to figure out how you draw a rectangle here. That's the hardest thing. And if I save this, then I should get a rectangle as a background. And it's just background because I put it first in my list. And now I can change this color to a nice color I invented before. And now I'm combining a shape and I'm combining a line, and it just works out automatically because I'm always using these domain units of sort of number of days on the x-axis, exchange rate on the y-axis. So you never have to fiddle with pixels. And I'm going to cheat a little bit and insert the shape for the second half. That's pretty much the same thing, really. And now I've got both halves filled. And the only thing I want to add now is to add some axes to this. I'm going to say again, shape axes. And I'll show you that I can put them on the right as well, which will make this look quite nice. So this is how you compose a chart. And now we're already going beyond the basics, despite sort of covering something like 5 different primitives. So that's the first thing. You can actually do a lot more using a few more primitives. So the next thing I want to do is to add a title to the chart. That's quite a useful thing to have for charts, and I didn't tell you how to do this yet. And the fact is, this is I don't really need to have anything primitive for titles. I can create title just by saying shape.text, and this creates a title. And here I'm sort of saying where to put this. Now this is where it gets interesting, because I now have title and the body, and the body is sort of obviously specified in terms of numbers of days and exchange rates. The title, I can just render the title to show you the title. Title just is something that has sort of positions from 0 to 100. So it's sort of made up scale. And the interesting thing I can do is I can combine these, obviously using layered. I have title and body, but if I do this, they're using fairly incompatible scales, so that the chart itself ends up just being somewhere in a tiny corner on the side. So there is a way of fixing this by saying, rather than sort of using the scales that are inherent in the shape, I want to use scales that I've explicitly provided here from 0 to 100. So now that the chart has span for the full width. And if I do the same thing for the y-axis, now I have to think about this to get it right. So this is going to take an area from 90% to 100%, and the body is going to be from 0 to 90. So now I've sort of explicitly positioned the things just by replacing their scales. So this is sort of more advanced trick that lets you do various combined charts that overlay each other and maybe share one axis but not the other. But it also lets you do things like titles. And really what's sort of interesting lesson here is that there are multiple ways of composing things. So I have this sort of basic layered operation that really just says sort of put things over each other. But I've got various operations to tweak these, like operations that somehow override the scale. And if you override the scale, the automatic layering will work differently. So there's an operation that lets you say, when looking at the shape, it has to infer what's the scale, and you can override that in various ways. So what are the sort of key ideas about functional thinking? First of all, I think it's really sort of thinking about the domain. So when you think about charts, you shouldn't be thinking about pixels because that's just a technical detail. You should be thinking about the domain primitives, like values in terms of years, exchange rates, and so on. You should be thinking about sort of domain primitives like lines and axes rather than pixels and polygons. You need to think about the different ways in which things can be composed. So in charts, that's mainly the overlaying. But again, if you look at other domains, there will be different things. And in F#, and this is sort of somewhat specific to this example, but a useful trick, you can use units of measure to make sure that you actually don't introduce certain errors. There's also, I think, somewhat more general design patterns that you can extract from this example. So I'll just talk briefly about 3 different design patterns that I think are very common in definitely in functional programming. I think they would be applicable to other areas as well, and they are nicely illustrated by what I was showing. So the first design pattern for that, I'm going to do one more change to my example here because I've constructed this chart with a title, but adding title to something is obviously a useful operation that I might want to do more often. So what I can do is I can turn this title construction into a reusable function, reusable primitive, where rather than just putting this text, I'll use arbitrary title, and I'm going to attach that to some body. So that's going to be here. So I'll say title, my text, and then the body for which I want to use the title. And well, actually, I'm going to render this. And in the title operation, I'm going to define the elements that define the title at the top. And I'm going to use this layering to combine that with some body that the user provides. I'm going to get some text and some body, and this function, the title function, is just sort of saying, whatever you gave me, I'll put a title on top. Now I'm going to change this just by adding some exclamation marks to see that this actually did change, so that works. And the really useful pattern here is that if you have basic primitives, like my layered and text and shapes, then you can kind of define different layers of abstraction. And in this library, this actually happens at multiple places. So at the very sort of lowest level, there is SVG and X and Y coordinates with pixels. On top of that, I've got my library of shapes, compositions, and categorical and continuous values. And on top of that, you could define fairly ordinary list of charts like bars and lines. And the main point is that sort of at any point, the sort of you can go down one level if you need more flexibility, but it's not like you're jumping all the way from very high bar charts to very low rendering of pixels. And in a lot of well-designed functional code, you have these sort of several layers of abstractions where the next one is built from the primitives just below in a relatively simple way, like we just built the title. The other interesting thing is there's often some kind of processing pipeline. So in my library, the way the shapes actually get rendered is that the library takes the shapes, calculates some inferred scales by sort of producing a new type, new value of scaled shape, then it calculates how's that's going to be projected on the screen. That produces another set of data attached to the shape, and then it actually gets transformed into SVG. So you've got this processing pipeline or rendering pipeline where a value goes through a sequence of transformations. And this is something that, again, happens pretty much everywhere in functional code. The compiler does this as well by taking your raw text, turning it into some syntax tree, adding types to it, turning that into bytes of compiled code. So again, this is another very common function pattern. And for the last pattern, I actually want to show you how you create an animated chart. So I'm going to take my bar chart from the start. That was this. So this was my bar chart. And I've got data for 2017 elections and 2019 elections. And I want to create something where you click and it will go from 17 to 18 by sort of adapting the heights. So the way to do this is I'm going to use an approach that's been popular in F# based on the Elm architecture, where I have some state. Now, in my case, the state is going to be just sort of 0 to 1 based on how far in the animation you are. You have some update function that takes a current state, an event representing what's happened on the screen, and returns a new state. So right now, this is not going to be doing anything. And I'll have a render function that takes the current state and turns, produces the HTML we want to see. So here I'm going to just wrap that as SVG, and I've got a built-in function that takes the initial state, rendering function, and update. So if I do this, then it renders a bar chart. So that works, but there's nothing really interesting here. And I can construct some more HTML around this. So this is using a tiny F# library for constructing HTML, where all I want to do is to create a button with a text animate, and I'll want to add an event handler. So when I click, this is going to call some function that currently will not do anything. So do I get my button? I got my button. Now I need to do the update of the state. So what kind of events can happen in this chart? There's something that happens when you click animate. So I'll have one event for animate, for start. And then I'll have another event that happens sort of every time you want to take the next step of the animation, sort of a next frame. I'll call this animate. Now in my update function, if I get the start event, then I'll just start by setting the state to something that's a bit more than 0. And if I get animate, I'll just increment this by a tiny bit. And whenever the user clicks the button, this is going to trigger the start event. And the other thing I need to do is to also trigger the animate event whenever, if my state is somewhere between 0 and 1. So if this is more than 0, but it's not 1 yet, then I'm going to trigger, then I'm going to set a timer to trigger the animate event after, say, 20 milliseconds. And because this is calling JavaScript function, it returns some null that I have to ignore. So now it will actually go through the animation, and I just need to do some more mathematics here to actually calculate the value of the bar so that it's sort of 2017 when state is 0, 2019 when the state is 1. So how do I do this? I'll take this times 1 minus state, plus this times state. And if my mathematics was right, then this should actually do an animation. Let's see if this works. Now, if I click here on animate, then it did actually animate. It sort of doesn't, you have to be very careful to watch it. So I'll show this again. 3, 2, 1, animate. But it did animate. It doesn't look great, partly because of this automatic scaling where the largest bar is always taking the full space. So I can do one more tweak here by setting the scale of this, and I don't care about the Y. I'll just say none here, but I need to override the default Y scale so that it is continuous scale from 0 to, let's say, 400. And then if I do this, it refreshes. I think I should have put this inside the axes, otherwise it looks bad. I'm going to change this, move this here. So now we'll have axis that goes all the way to 400. If I click animate, then the bars will shift. So that was an example of how you do an animated chart, but really the point of this was to show you this useful general functional design pattern of states and events, because what happens in the implementation is you start with some state, an event happens, you transform that state into a new state, then you can render that. Some more things happen, you transform the state again through an event, and you get a new state which you can render. And this happens for different events, like clicking the start button or just updating the animation. And this is something that got really popular in the user interface programming through the Elm-based architecture. And then if you're using F# and Fable for web programming, there's an Elmish library that implements that, which also now has a mobile version and so on. So it's popular in UI, but it's also kind of the essence of event sourcing. So it's really a pattern that I think appears in many different places. And here I've used it in the context of charting to handle the animations where you go through several states. So that's almost all I wanted to show you. There's one last bit that is interesting, and this is the fact that not everybody actually uses F# and Fable for doing their web programming. So the library that I've been talking about, it's called Compost JS, and you can find documentation online. And this is actually a normal JavaScript library. So this fact I've been hiding from you so far to keep you looking at my F# code, but the library I've been showing here, there's a tutorial on how to use it from JavaScript, and it gives you a variable or JavaScript variable C, and then when I create column, you can see exactly the kind of things I was showing right now with F#. There's a way to overlay columns, just like what I've been doing. There's a way to set fill colors and so on, and you can sort of draw various things. So really this whole thing, even though it's written in F#, it just appears and behaves like a JavaScript library. And the way this works is that I'm using the Fable compiler to turn F# to JavaScript. And Fable integrates really nicely with all the standard Node and JavaScript web development tools. So it lets you compile code into JavaScript, package it through Webpack, publish that to npm, and that's basically what I'm doing here. The only interesting thing is that to make the F# code really sort of nicely usable from JavaScript, I did add a very lightweight wrapper around it. So in the source code for the library, there's a definition of an interface, which is a way of creating a plain JavaScript object that has all these different primitives that I've been showing you in the F# side, has sort of a JavaScript version. Now, most of these things don't actually do much. They'll just sort of call the F# thing. The only difference is in some cases where the JavaScript interface is sort of gets easier if you just let it take different types. So in some places in the interface here, I just take object and then I use some JavaScript tricks to find whether it's a number or a string. And then based on that, I can do the right thing automatically. So the JavaScript API for it ends up being actually a somewhat shorter than the F# API. So if I wanted to show you this, I'll just have to switch my my project so that it starts my JavaScript demos. And if I go to the right window and start it again, now this will actually show you the process as well, because when I'm building the library, it just starts a Webpack server so that I can do my live debugging and live updating. And Fable is the F# to JavaScript compiler, and that has a Webpack loader. So whenever Webpack notices an FS file in your project, which is what I was doing here when I just had .fs here before, whenever Webpack notices that, it will trigger the F# compiler, which will then find all the relevant F# files, compile them to JavaScript, which has just happened, and I think now it's all loaded. If I go to the right file, that's this one. This is a file with various demos, all implemented in JavaScript, ranging from some helpers, ranging from the very basic ones like creating a bar chart by mapping over all the elections data and generating a column for each, all the way to what I was just showing here, an animated chart with some initial state, update function that reacts to events, a render function that does something in response, and a sort of entry point that says start with this state. So the very last one here is actually quite fun chart where it shows you the UK government spending on different things for year 2015 as a percentage of GDP. And the idea is that you first have to make a guess. And once you make a guess, then it will tell you what's the right thing. So you might think that the UK definitely doesn't spend enough on education. The health expenditure is great. Social protection, I don't know. Economic affairs, I'll just put some values here. But if you actually do this yourself, you have to sort of figure out what do I think, and then when you click show me how I did, you'll see what the actual reality is. And in this case, the biggest single bit of expenditure is pensions, so that all goes under social protection. The point is, this is something I can actually compose from the primitives I was showing, and this chart has a few sort of extras, like these bars that indicate your original guesses, but that's really just drawing a line. So there's nothing extra. So to wrap up, the talk was really, so I talked about designing composable libraries for data visualization, but data visualization is really a sort of example domain to use to illustrate more general patterns. And the first question that I think is very fundamental is, what is it that we're actually working with? So this led me to this whole sort of discussion about what is a chart, what are scales, and I think this is something you really have to do no matter what kind of software you're writing. In functional languages, very often this maps to defining primitive types. So doing sort of a domain modeling using things like F# discriminated unions, which let you say a scale can be categorical or continuous, and you sort of list the different options, and it often fits on a slide, so it's something you can explain to other people in the team and review that. And as a bonus, I've used the units of measure in F# to make sure I can actually implement it with my limited projection mathematics skills. And the other thing I did demonstrate throughout is 3 valuable functional design patterns. First one was this sort of building up of abstractions. If you have nice composable pieces, you can define more high-level abstractions like adding a chart title or defining a bar chart, really just by putting a few basic things together. So you have sort of multiple layers with relatively sort of low friction between them. I talked about how you go through transformations, how the sort of shapes get rendered by starting with the shape, calculating scales, calculating projections, turning that into SVG. So that sort of sequence of transformations, again, really, it's sort of, you have multiple steps where there's relatively low friction between each two. And finally, when showing the animation, I talked about the states and updates, which is a very useful pattern for UI programming, but it's also the same idea that appears in event sourcing. And the library is available as open source project online. So if you search for Compost JS, you'll find it, and you can look at how the whole thing works. And I think it's a nice example of doing quite useful thing in F# where you use F# and functional programming for implementing something that's quite tricky, and you have to do a lot of thinking about the domain, but exposing that as just a simple JavaScript library which anyone can use. And I think that's great. So that's all I wanted to say. Thanks for watching. And if there are any comments, post them into the chat, or I'll check the Slack later on as well.